Alright, so these first couple of pages have established that for a cylindrical pressure vessel, you have hoop and axial stresses that are not equal, and it is twice as big in the hoop direction. And if we take this case for a spherical pressure vessel, because of the symmetry, we actually end up with stresses in any direction, regardless of the direction that we take the slice, is the same as the axial direction for cylindrical. So it's stronger, it's a better case. One way that we can make a cylindrical pressure vessel, which are typically easier to manufacture and easier to deal with, is to take the hoop direction and support it and make it stronger than just the material is by its own accord. Doing that by wrapping with carbon fiber or any kind of composite to support that hoop direction and take that load. So now moving into a little bit of material that's relevant to the pressure vessel lab that we'll be doing is thinking about these stress-strain relationships now that we have loading in two directions. This pressure gives us load and therefore stress in both the x and the y directions. So far, when we've dealt with the relationship between stress and strain, we have had this case right here, a plain old Hooke's law. However, this Hooke's law is valid only when loading is in the axial direction. We've got a little bit more going on now, and we need to think about what's happening in both directions. So if we have our section of material and we consider what's happening because of this applied stress in the x direction, we know that we expect it to get longer in the x direction and we expect it to contract in the y direction. We expect that the strain in the x direction is proportional to the stress in the x direction, but we know that Poisson's ratio enters the picture when we start talking about the strain in the y direction, and that is the negative Poisson's ratio times the strain in the x. That how much it shrinks in y is proportional to how much it grows in the x direction. But we can also say that it is related to the stress in the x direction as well. Okay, so we have strain in x is proportional by the modulus of elasticity, and the strain is y is proportional to both Poisson's ratio and the modulus of elasticity. Okay, if we now think about the contribution to the strain for our stress in the y direction, we know that our structure is expected to get longer in the y direction, shorter in the x direction, and we can write the same relationships. That our y strain is expected to be related by the modulus to the stress in the y direction. The stress in x is the negative Poisson's ratio times the strain in y, or casting that in terms of the stress in the y direction, we again have this negative Poisson's ratio over the modulus times the strain in y. The third thing that we haven't discussed in quite a while is what about the shear stress and the shear strain? That shear stress is equal to the shear modulus times the shear strain gamma, or if we're talking about these in terms of the shear strains, we can simply solve this as gamma is 1 over the shear modulus times the shear stress. So now we can take these expressions and end up putting them into a more compact matrix form. So what we want to end up with is a matrix formulation that has our stress in the x direction, our stress in the y direction, our strain in the x direction, our strain in the y direction, and our shear strain in terms of the corresponding stress in the x, stress in the y, and shear stress. So to simplify our life a little bit, we can think about the expressions. We have strain in the x direction, if we look at the first expression on the other page, is 1 over the modulus times the stress in the x direction plus nothing times the stress in the y direction plus nothing times the shear stress. The second expression is the negative Poisson's ratio over the modulus times the stress in the x direction, nothing times the stress in the y direction, and nothing times the shear stress. Then we move to the strain in the y direction is equal to nothing times the stress in x plus 1 over the modulus stress in y and nothing times the shear. We have another expression for the strain in x, which is nothing times the stress in x plus the negative Poisson's ratio over the modulus times the stress in y, and nothing for the shear. And then our last one, gamma xy, is no x stress, no y stress, and 1 over g times the shear stress. So if we now put those into our appropriate locations in our matrix, too much, we will see from the first equation we get a 1 over e. From this fourth equation we get a minus nu over e, and from none of the equations we get a 0. From the second and third equation we see we get a minus nu over e in the first position, 1 over e in the second, and zeros for the shear stress. And for the gamma, nothing for normal stress in the x direction, nothing for normal stress in the y direction, and a 1 over g for the coefficient of the shear. Now, we now have this matrix formulation for our stress-strain relationships. But what do our strain gauges measure? We measure our strains, not our stresses. We need to solve these so that we measure strains and we get stresses out. And because these are uncoupled equations, we can solve these in closed form, and we end up with these two expressions which we can solve for stress in the x, is the modulus over 1 minus nu squared times this combination of the strains, and that the y stress is equal to the same coefficient times a combination of the x and y strain, and again decoupled, that the shear stress is equal to the modulus, the shear modulus times the shear strain. With these equations, we can now move into an example problem. So coming back to what are the stresses and strains in the wall of a cylindrical 10-inch in diameter pressure vessel pressurized to 500 psi. We're going to say that this is steel with a modulus of 30 million, a Poisson's ratio of 0.3, a diameter of 10 inches, ends up being a radius of 5 inches. We have a pressure of 500 psi, and we know that the wall thickness is 0.0747 inches. First thing, this is a cylindrical pressure vessel, so we can use our equations. The axial stress, PR over 2T, 500 psi times 5 inches over 2 times the thickness, 747. So we have an axial stress of 16,733. We know that the hoop stress is 2 times the axial, so we have 33,467 psi. Now, the expected strains in the forward direction, or strains as a function of stress, we have the x direction stress over the modulus minus Poisson's ratio times the y stress over the modulus, or pulling out this term, if we consider our x direction, our axial direction, we can say that our axial strain is equal to 1 over our modulus times our axial stress minus Poisson's ratio times our hoop stress, 1 over 30 million times our 16,733, 0.3 Poisson's ratio, 33,467 psi. We expect an axial strain of 0.000223. For the strain in the y direction, which we can also say is the hoop direction, that will be the hoop stress minus Poisson's ratio times the axial. So 1 over 30 million times our 33,467 minus Poisson's ratio times the axial stress. So we expect strain in the hoop direction that is 0.000948. So summarizing, we have stresses in the axial direction about 16,700, in the hoop direction twice that, 33,500, and strains, if we report them in microstrain, which is like the indicator boxes in the lab, we have axial strain of 223 times 10 to the minus 6, or 223 microstrain, and in the hoop direction we have 948 times 10 to the minus 6, or 948 microstrain. Again, this is taking it to 500 psi, which is well beyond what the shop air can do. And I guess another note is that this thickness of 0.747 is a standard 14 gauge steel sheet metal. Very often they put these pressure vessels together, as you can see from the sample that we've got, the air tank in the lab, that they are pulled into basically half of the vessel and then welded together, and then welding on end caps.